Okay, we started. Okay. Welcome back to this afternoon's program. We're going to be starting off just right now with the data analysis section. So I'm assuming no more blue sky. Clouds are gray and cloudy. Our first speaker is Daniil. I had your last name, Kazantsev. He's going to say it again and correct me. It'll be great.
Thank you, Peter. Yeah, hi, I'm Daniil Kazantsev. Like this? Got. Yeah. I'm data analysis scientist at Daniil Lightsource, and we're developing this new project called HTOMO, stands for High Throughput Tomography software at Diamond. So at Diamond, we basically have 3 dedicated beamlines collecting tomographic data. And what type of experiments we have there is one standard scan in 180 degrees, then double field of view scans or 360-degree scans when you need to do some post-processing data stitching to convert it to 180. Then we also have in situ scans where something is dynamically changing under control conditions, for instance, or 4D tomography, helical scans when the sample is vertically outside the field of view and we need to shift it. Then also a variety of experiments where rigs, for instance, involved, and there are limited angles, so missing wedge, also laminography, phase contrast imaging, sometimes also leads to tomography, where tomographic reconstruction required, and also raster scans like with pencil beam, but the amount of data there collected is usually smaller. So a typical data set that we're working with is 40 gigabytes in size, 60-bit data type, so approximately 3,600 projections collected in 3D plus time setup. There could be hundreds of gigabytes, sometimes terabytes, when you need to perform hundreds of scans, obviously. And then the data after experiment is stored at the general parallel file system, GPFS. Then software that we use to do data analysis and reconstruction usually pick up the data from the GPFS system and employ cluster resources, which include CPU and GPU cluster nodes. So initially, there's quite a lot of different packages, most of them open source packages for tomographic analysis and reconstruction. So I'm probably quite familiar, people who are involved in tomography industry, with TomoPy, which is a library of modules written in Python. The one to the left, which is called Savu and HTOMO, that is currently being developed at Diamond. HTOMO is currently being developed and Savu is in production. So Savu started in 2014 as also a Python package using MPI protocols and parallel HDF5 file system as sort of a backup for a memory limitation. So there were not a lot of memory at the time on the nodes. So every processing step in the package going through the disk. So effectively you're writing and reading from HDF5 files. So it's heavy bounded I/O. And most of the methods in Savu, they're integrated and kind of linked with the framework. So you need to know a little bit about the framework in order to write a plugin for it. So for HTOMO project, we came up with a certain set of rules or requirements that we would like to change. So essentially with Diamond 2 upgrade approaching, we started thinking about the scalability of software, tomographic software, working with larger data, so we need some kind of high throughput, then potentially in-memory compute rather than the disk, so we would avoid this I/O bottleneck, and compute on the GPU as well. Then the methods should be kind of external libraries that we just plug, so we do not sort of copy-pasting them, if you like, or rewriting them and integrating in the software. We just use what's already there, for instance, TomoPy, which is purely mostly CPU package. And then simple UI as a kind of independent replaceable layer. At some point, we might want to do some kind of GUI, for instance. So that should also be a different layer. And implementation using more like new Python features and libraries. Then we come up with high throughput tomography software, HTOMO, in 2022. And essentially, it's got a few kind of main things, or like concepts, if you like. So we work with, rather than two-dimensional slices, we work more with 3D data chunks or 3D blocks that would fit into a GPU memory. And we perform the computations on the GPUs in a memory-aware fashion. I will be speaking more about it later on. But essentially, we need to know the size of the GPU available and the amount of the data we could fit on it. Then the methods should be chained together. So if we use GPU methods, that we can essentially serialize them in some kind of chain and keep the data on the GPU as long as possible. Then we will use external libraries as backends and provide human-readable UI. So we kind of choose YAML for now. So chunks and blocks are quite important concepts. So it's an MPI-based software that we're developing. So we've got a big data chunk. And then, for instance, you've got 4 MPI processes. They will split this data onto 4 processes. Each chunk will be associated with every process. And inside chunk, you will have blocks. The blocks will be essentially a loop of blocks. And the block size should fit the GPU memory available. There are different things that we need to do on the CPU, unfortunately. So nothing fully can be done on the GPU. So we, for instance, need to reslice the data. So working in different some kind of in different slicing patterns. So we might work with projections stack, or we need to reslice and work with sinogram stack as well. Different methods work for different patterns that we call them, like projection, sinogram, or then the pattern doesn't matter. For instance, a 3D filter would be all in our language. Then this quite important concept is the GPU memory estimation. So because we want to know the size of the block that would fit the GPU in hand, we need to calculate a memory requirement for every method. We need to know how much of the memory available on the GPU, and then in our chain of methods, we need to calculate the memory requirement. So this is done separately as well for each method. So then also a concept of section. We will kind of structure the pipeline execution order, so it's all done by framework. Then the methods in that particular pipeline will be also chained together. That's all kind of taken care of by the framework. And when the data needs to be returned, we work with CuPy as an API. When it needs to be returned to the NumPy array, that's also been done by framework. So we call this kind of idea of data source and data sink. And it could be memory, CPU memory, or it could be a hard drive. So if the memory is not enough, for instance, data is too big, or you've got a laptop, then you will use hard drive instead, and data source and data sink will be the hard drive. So it will obviously significantly slower than to go through the memory. I'm talking about an order of magnitude slower. Then, because we use the external libraries, we use TomoPy. We started with as a CPU library, and then decided to accelerate some of the methods on the GPU using CuPy and CUDA. We created 2 additional libraries, which are on CPU, HTOMLib and HTOMLib GPU. It's on just methods on GPU. And we're mostly using them because, yeah, we'd like to keep the data on the GPU as long as possible, so mostly using GPU methods. And there are different wrappers for that because there could be different cases for tomographic processing. There could be kind of generic wrapper, which is the kind of filter, if you like. input in, input out, nothing changes in terms of data dimension and so on. And then could be a normalization wrapper when you need additional data like floods and darks. There could be centering where we just need to find the value and pass it on along the path later on to the pipeline. Then it could be a reconstruction wrapper when you've got the sinogram, then you need to know about geometry, angles, and etc. So and then just image savers, so saving TIFFs, for instance. There's no output whatsoever. Then for our YAML interface, we kind of chose slightly GitHub Action-ish language with the references to some parameters that's been estimated along the pipeline. For instance, center of rotation is saved into the side outputs, for instance, and then referred to it later on in the reconstruction. Those YAML templates, they're automatically generated for every method and put on documentation. And we also have a tool that checks the validity of this YAML because the users could input things, not with some errors and so on. So just quickly through some benchmarks that we've done recently. Essentially, we're running our code across on one node or across multiple nodes. So we've got this quite simple pipeline with a loader, normalizer, center of rotation estimation, Pagani filter, stripe removal, reconstruction, and 3D median filter afterwards. So we're talking about a minute and a half for 20 gigabyte data using one node for V100 GPUs. And you can reduce that time twice when you obviously go across two nodes, but then the time slows down. So essentially, it's not necessarily feasible to use more than two nodes in this case. It's still possible because it's just MPI code. Then, as I mentioned, some of the methods were accelerated. So we're talking about acceleration sometimes hundreds of times, but it's just not necessarily mean that we were so good at it. It's just the code itself might not be optimized in the first place on the CPU. So we're using that. But the biggest bottleneck so far is actually still saving the HDF5 file, which is chunked kind of horizontally, if you like, sinogram-wise. And then it takes a significant amount of time, and we're currently looking into it. So talking about 120, so 2 minutes. And saving images as well. Thousands of TIFFs take half a minute, and FBP reconstruction as well. For future direction, so it's not currently in production, this HTOM development, so it's been 2 years so far. We're planning to do this maybe during the financial year, not the other year. So, and integrate into beamlines that we support, and as well get the feedback from them, so it's some kind of possibly agile loop to some extent. Testing and fixing things. Then we'll look into the further optimization of performance and potentially faster HDF5 saving. And we also have the ZAR saving option, but it's not necessarily faster than HDF5 so far. Then we do processing in 32-bit, so the data has been converted from the loader. And there's no sometimes need to do that, so the data could actually stay in 16-bit, and there are software that's like Tomokupai, for instance, supporting 16-bit, so we can save a little bit of memory and time on that. Thanks to the team. Questions, please?
May have to borrow. So are there questions? We'll just run back and forth. Oh, here, you can hold that one. Are there questions? Yes, sir. Here we go.
So you talk about HT-Tomo wrappers, which means that you would perhaps be able to integrate other backends rather than only the TomoPy one?
Yes, so essentially, is it working?
Yeah, don't come back.
Yeah.
You're going to hold it close.
No, take this one.
I hear my own voice. Oh yeah, now I can hear it. There's no limit essentially to what you can integrate as long as it's an importable library that you can call a function that has parameters. So we tend to generate these templates for the users, so they're not generating them themselves. So it has to know some kind of doc strings that you can get parameters from in order to generate that. But apart from that, there is no limitation. You can essentially, you need to do that, and then you need to add a little bit into the library in order to HTOM understand that it's a CPU or GPU method, for instance, but it's quite basic as well in YAML. That's kind of developers' side of things that we should take care of.
So in the interest of time, I think we're going to call it there. Thank you again.
Thank you.